I'm recording.
Perfect.
Okay, here we are. So again, welcome, Emanuela, and it's now your time.
Okay, thank you very much. Thanks a lot, Leah and Michelle, for organizing this. I'm very thrilled to have been invited, actually, and to be able to meet with you guys and with this all the people that are online right now. I when they asked me, what do you want to talk about? What do you think you could give a lecture on? I thought about the rheology of particulate gels and jump soft materials. That's how it came right to my hand. It's literally for me a bit like saying 42, right? Because it's really about the meaning of life, of the universe, of everything. And I realized then putting together the material for this, that it's a bit vague and a bit going in all directions. So that's what I'm going to give you, actually, very much in the spirit, I hope, of this Hitchhiker's Guide to Rheology. And so I'm going to try to give an overview of the questions and the problems I am interested in when thinking about these materials, and in particular the rheology of these materials. And hopefully I will give you a sense of how the issues that I will discuss connect to all sorts of very interesting properties that then are very important for our practical life, for things that we use every day, for things that we want to make better, and for things that we hope to be able to use in the future. So I have organized the material in sort of three pieces. The first part, it's more of a personal overview of the rheological behaviors and the phenomenology of these materials. Basically, I've thought about using more of a visual format where I can start from some observations in experiment to introduce some concepts and ideas that I think are important for this system in a relatively intuitive way, just to make it easier to follow this thing, in the Zoom format. And then if I have the time, I would like to talk about something more specific concerning the particulate gels type of materials and a couple of, and I would like to spend a few minutes discussing questions that are very interesting that are emerging and have emerged in the context of the yielding of jammed soft matter. So I would like that people feel free to interrupt me and ask questions. I realize that in my window here, I don't actually see the chat. So and I don't see the hands, unfortunately. So
Okay. I will tell you. I will tell you if
I
that
need you guys
comes.
to
Yeah.
interrupt me and say, I think in this form, it's better if we can do it like that. And, there are people that can ask questions, because I'm going to try to connect things that maybe not so obviously connected or, sound vague on certain things. So hold me accountable and ask me questions about the things that I am talking about. Okay, so let's start from, from this first part. So one of the difficulty in trying to understand the rheology of, and I would say the mechanics in general of this type of materials, is that you have materials which are made, I basically refer to particulate gels and soft jammed materials. And these are materials that in most of the cases have disordered microstructures. In many cases, they're sort of made of small particulates that can aggregate that have polymers that are constituted by polymers or proteins or colloidal particles or little grains that can be sticky or not sticky, soft particles, microgels, and so on. And so one of the difficulty is really to, for example, just to start by understanding, okay, how do I make sense on the basis of what I know from this the constituent, these small components, how do I make sense of their mechanical response, really starting, for example, from their modulus and their mechanical strength. And here I have a couple of examples to show you these challenges, right? This is experiments. I hope you can see my cursor. So,
yeah, we can.
We can, yeah.
So this is an experiment measurements done by the group of Gareth McKinley and Michaela Jeribon, Kesha Schwartz, and Thibault and their collaborators, where in fact they were able to perform experiments that were following the change both in the viscoelastic, in the loss modulus and the storage modulus as a function of time. Sorry, here I missed as a function of the frequency. Sorry, here I missed the label on the x-axis. As a function of the frequency as the time goes by. So in some cases, you have thermal fluctuations that brings the particles together, they start to aggregate, they form structures, and their rheological response evolves, and it evolves on a relatively rapid time scale. Here in this case is over hours. And the other thing that is remarkable is that it evolves by orders of magnitude. So then in these type of systems, the question of understanding what is the rheological behavior, just characterizing it, and then ask the question where this rheological behavior come from in order to design it, let's say from the microstructural components of the material or by processing the material. It really requires, devising new experimental techniques and also models and theories and simulations that can in fact make sense of this type of behavior. And you can see that the viscoelastic response really changes by orders of magnitude. And the viscoelastic spectrum, so the time scale that are involved in this time, the response of the material, also bridges over orders of magnitude in frequency and therefore in time. So this is, I think, a good example of the type of challenges and questions that one is after when trying to understand this type of material. A very interesting aspect of this is the fact that in this type of behavior, I can understand I can know pretty well sometimes what is the single components. Here I have in the bottom an image from confocal microscopy for model version of this type of particulate gels. This is a colloidal gel studied by Mike Solomon some years ago in this paper that it's really beautiful, where they did some microrheology to try to connect the microscopic dynamics that they would see to the type of structure that the gel has. And they were trying to draw to identify correlations, connections between the way the distributions of the displacement now just due to thermal fluctuation changes across the material as the structural heterogeneity changes. So some of this evolution that we see here, it's not due only to the fact that the interactions between the particles can evolve, but it's really due to the fact that the structure is developing in different ways, and it's developing over a broad range of length scales and therefore time scales. So you see how understanding the development of this type of rheological response is actually can be challenging and very interesting at the same time. So, sorry, let's see. Yes. So in fact, one theme that has been emerging is that even when I can image the structure, like in the beautiful experiment of Mike Solomon, and this is the image that I have here. This is another confocal microscopy image from now. This is the first group also with the Mike Solomon, and this is a work also with Lilian Xiao and Jim Swan, where in fact they could see that some of this the rheological response of this material, and here we're really talking mainly about the mechanical strength and the moduli, so even linear rheological response. This is, in fact, they could realize how you cannot, in fact, understand the rheological response that you see the modulus of the gel as you vary in this work. They were varying volume fractions and interaction strength between the particles. You cannot understand it if you don't realize that there are some structures that have been built up in the aggregation of the gel, that the gel can be seen as some network of clusters. And you really need to understand how the clusters are connected with each other in order to predict the rheology of the whole gel. And this is an idea that I had worked on a bit with also with Alessio Zaccone and Hua Wu in Zurich at that time when I was at ETH, because we actually had worked with the idea that in some of these gels, the intermediate step of the formation of the gel network go through formation of clusters. And then these clusters get connected into this larger scale heterogeneous structure, like the one that you see here on the top. But I think that you can see some of the structures also here on the left, right, in the lower left corner. And so what we had done is to analyze some of these experiments by comparing, okay, what is the modulus that you would get if you took just the interactions between the particles? And this is this horizontal line here. For two different systems that they had different interaction strength. So you get two different lines for the modulus. But obviously this modulus doesn't change or doesn't change much if you change the volume fraction of the particles. However, if you consider, however, your experimental data, and now these are experiments from a couple of different, for a couple of different groups. And now this the experimental data, instead, you can see this is the moduli measured, and you can see that the modulus changes quite a bit as a function of the volume fraction of the particles. And we realized that you could actually understand and capture this type of changes if you instead think not in terms of the interaction that connect the particles, but instead you think in terms of the connections between the clusters. So now you have bigger objects that form your, let's say, solid. And what you care about, what the elasticity seem to care about a lot, is the connections between the clusters. So I have now these two themes that are emerging from just these two things that I told you. One thing is that there is evolution over time because the structure is building up. And there is, and this build up comes with a lot of structural heterogeneities, which then determines different distributions of characteristic times. And this is what contributes to the complexity of the rheological response I was talking about. But then there is some structures that I can make sense of sometimes when I can image it, right? And there is a subset of this structure that actually it's important and dominating, for example, the mechanical strength and the modulus of these systems. So there is this this idea that in order to understand the way the modulus develop in these materials, I need to understand what is the path through which the gel form, and therefore, which is the type of intermediate structure the gel goes through. And even when I do that, I really need to have some good ideas of what is the part of these structures that in fact controls, may be dominant in the elastic response. And this can change, of course, over different timescales. But how do this timescale emerge? It's a question that it's still open, and I want to say something about this a bit in the second part. Okay, another very important aspect that I need to worry about when I want to understand the mechanical strength of the material, and is the fact that I'm not forming, whatever is the solidification path that I have chosen. It could be by adding a depletant to my gel material or compressing my suspension of particles to make it solid, or adding salt to induce aggregation. In any case, I'm not forming a crystalline stress-free structure. I'm always forming some stressed type of structure that is responsible for the stress transmission. And so that's my little cartoon here. If I think about my, representing this complex gel as a bunch of little particles connected, or beads connected by springs, my springs cannot be all relaxed at their rest position, but they will be compressed or stretched depending on what is the history that the gel goes through. And this is going to have an impact on how the material responds, how the material in fact evolves just at rest, because there could be some relaxation over time due to a little bit of aging of the structure of the system. Sometimes it's aging of the structure, sometimes it's aging of the contact. Most of the time, it's going to be both together. And then when I apply a stress or a strain on this type of material, when these materials are subjected to a load, these type of stresses are going to also want to be relaxed, and they are going to contribute to the way the material respond to the deformation. So these are the type of things that we need to think when we try to understand and make sense, and that I would like you to have in mind when you think about the rheology of these materials. So let me give you an example. And this is a calculation that I did with Xiaoming Mao and various collaborators, where we computed the modulus in a very jammed suspension that we had prepared in the simulations with different cooling rates. Okay, now this is a simpler version of the solids that I was discussing before, because I don't even have sticky interactions and I don't have a complex aggregation path that can be there. We just prepare, in fact, these repulsive particles that are soft so they can overlap, and then we compress them until they become solid, right? And as you do that, if you try to, then you get, your stretched and compressed springs that you have here, and deformed stress configuration, and you try to calculate the modulus from all the springs that you have there, because you know all the forces between the particles and all the positions of the particles. So you extract the modulus from here, and you can see that the modulus that we actually measure if we do a mechanical test in the simulation, a linear viscoelastic test to extract the low frequency response of the system, and this is this purple data down here. But if I don't include, if now I want to compute this stress, just knowing what is the spring constant that's come from the interaction, from the fact that the particle overlap and their positions, then I got this data up here, right? If I don't put in any information about the stress. So if I don't put in any information about the fact that the springs are pre-stressed by the way I've prepared the system. And so you can say, okay, it's a small difference, but and it's in these reduced units, so it's not so easy to grasp. But we know that in hard material, pre-stresses can be and frozen in stresses in solids can be huge, and in soft materials they can be maybe smaller, but they are often comparable to the modulus itself. So they really have to the interaction strength of the material itself, because the material is soft, and so they can really affect the response of the material a lot. And these are with the other data that you see in this plot are other attempts that we tried to get better at this estimate. For example, if I consider the fact that I should at least correct my modulus by the fact that now my system is not at zero pressure because I have compressed it. So I get this orange data here. It goes in the right direction, but it doesn't get it quite right. And it's only when we, in fact, when Xiaoming Mao and her group designed a specific approach to include pre-stress in the calculation of the modulus from all the springs and the normal modes of the gel, that you get actually, you start to get a value of the modulus that gets significantly close to what we have measured in the simulations directly from the mechanical response, and that seems to follow the same dependence on the cooling rate, so capturing, in fact, really what's happening in the development of these type of stresses. Okay, so the fact that there is this formation of structure, if I go back to my particulate gel and the way they come together, but also in the case of the more homogeneous jammed soft solids, it does produces naturally a range of time scales and some characteristic length scale in the systems that are kind of difficult to extract, even when I'm able to see the microscopic structure. So I showed you those images of the colloidal gels because there we can see some structure. It seems we should be able to really make the link between the particulate matter that compose the gel and the type of structure that emerges, for example, during the gel formation. But understanding how the different structure actually can lead to the full rheological response. If now I don't want just to describe the modulus, but I would like to know also how the system behave over time, then I really need to understand, to go to things like analyzing the microscopic dynamics. And there is a lot of insight that has been gained, for example, doing scattering or following the evolution of over time of the particle motion. In gel, there is a large literature about that. In fact, the map that I was showing you before from the experiment of Mike Solomon on the PMMA gel and the colloidal gels, those were in fact obtained by combining imaging and microrheology. And here, this is an example of a very famous experiment where people were measuring the scattering, the intermediate scattering functions. So how the scattering intensity basically changes over time for different wave vectors in these aging gels. And you see that, okay, these relaxation functions that basically tell you how the density fluctuations change over time. So how the relative positions of particles in my gel change over time, and how they do that in a very complex and heterogeneous way. But in fact, it's particularly interesting because it tells that this type of results, they tell us that the dynamics that you can see, it can be slow, right? Which is what we expect because the particles are trapped in the gel, but also characterized by this kind of abrupt relaxation. This is what you see here in this decay. If you have an eye trained to stare to a lot of exponential decays or stretched exponential decays, and you have an eye to diagnose what is the shape of this function, then you start to notice that in fact, there is nothing happening in this relaxation for quite a long time, but then the decay is quite abrupt. And in fact, it's this type of decay that has been measured, I think, one of the first time in these experiments, but there is by now a large literature on that, is actually faster than exponential. And this is due to the fact that as I build my structure through the gel formation, I build a network that is able to support stresses and to store elasticity in these type of systems that are soft. And that's why when stresses relax during the time evolution of the system, actually the motion of the particles can become actually faster than diffusive. And this leads to this type of a relative abrupt and super diffusive or compressed exponential type of relaxation. And this is in fact what we have seen in our simulations, where in fact we could mirror exactly this type of behavior some years ago in a model gel where we were simulating the aging by cutting connections in regions where stresses, for example, were higher. As you cut and if you are in a regime where the thermal fluctuations are very weak with respect to the strength of the interactions, then you start to see basically that the gel snaps back, right? There is like a rubber snap effect, which gives you this type of abrupt relaxation. And for example, a characteristic time that is plotted here as a function of the wave vector. So now I'm measuring the characteristic time over regions of different sizes that are determined, basically, that are selected by the wave vector. And I can see that in this elastic regime, the relaxation time, in fact, grows as I decrease the wave vector. So it grows as I increase the size of the region that I'm looking at as 1/q, not 1/q squared, which is what I would think would be happening if the dynamics of these particles was purely diffusive. But in fact, it's 1 over q, so nearly quasi-ballistic, and in fact, really due to the elastic recoil of the gel network. So this elastic recoil can, in fact, relax a lot of the stresses if I don't have other sources of relaxation. If my system is very jammed and tense in this gel structure, when I remove connection, I will see this type of elastic recoil. And what's interesting is that this type of dynamics is also sensitive to the multi-scale structure of the system. You can see that I have a certain type of dependence up to what we knew in the simulation was sizes of the order of the mesh size in our gel network. But if I go to smaller wave vector, then basically I start to see that the system is homogeneously responding or is homogeneously relaxing, and this is because everything is elastically connected. So paradoxically, when I go to even larger length scale, everything is coherent and relaxes coherently because now everything is connected in my giant elastic spring. So this has consequences. This is what I'm talking about here is just an insight into the dynamics of this system at rest, which contains information about this type of processes. And I can imagine that now if I apply, as I was saying before, if I apply perturbation, if I'm looking at the behavior of the systems, even under flow, I should worry about what are the type of stress relaxation mechanisms that emerge if this is what basically the structure is built to do, right? And so this is a very, another beautiful experiment by the group of Sébastien Manville, where basically they imposed a cyclic varying stress to induce the fluidization of the gel. And then they were studying how as a function of the number of cycles, so as a function of the time, they would see the viscoelastic response of the gel change, and this is what is plotted G prime and G double prime. And so you can see that over time, basically as they are cycling through the stress, they can see that the gel actually fluidizes, right? G prime becomes smaller than G double prime, but it does so in steps, quite abrupt steps, telling us again that there is in fact, a multi-level structure that is pulled into the fluidization of the system as time goes by and as the deformation is applied, or the stress in this case is applied cyclically. And I have this image here, which is from the work of Rosanna Zia from some years ago, where again they were doing this in simulations. They were applying stress and watch the gel basically creep and creep in with a very interesting type of dynamics, depending on where they were in terms of strength of interactions and frozen in stresses that they had in the structure. So at this point, it has emerged as a very important question to ask, is what is actually the microscopic dynamics of the system under load in more detail. And this has now become possible thanks to experiments like the ones developed, for example, in the group of Luca Cipelletti. This is by Luca Cipelletti, Lorenzo Ramos, and Stefano Aime, that built this shear cell, which combines a possibility of doing stress-imposed studies with scattering. And so you can, in fact, measure the rheological response, and then you can measure the microscopic dynamics. And in particular, the way the cell is set up is to measure the displacement of the particles that does not simply follow the deformation. So the idea, you know, before I was talking about the history of the system, the stresses that are frozen in, I think that if you think about this and the time scale over which the system evolves and the type of interesting dynamics that the system can have because it has the capacity of storing elastic stresses and relaxing elastic stresses. So what is interesting is that now I think you can see how if I start to apply a load or deform this type of material, those regions that were compressed or stretched, naturally they will not necessarily follow the deformation that I have imposed. And the fact that the system can have regions that can be more or less affected by what happens at the boundary, which is where I'm applying my deformation, will naturally produce a significant amount of non-affine motion. And so the non-affine motion, so the motion that I obtain, that I can have access to if I subtract what I would normally have if my whole system would affinely follow the deformation that I have imposed, the non-affine motion contains very key information about those phenomena that I was talking about. And so these type of experiments that have access to that are extremely important at this moment when we ask this question and we try to connect the type of microstructure that I have to the forces that produce that, to the kinetic path that brought the material have, or the type of processing that brought the material have, and then what happens to that when I apply a deformation. That's exactly the interplay that I think it's the most interesting thing to understand at this moment in time for us, both in terms of characterization, but also in terms to devise theories and theoretical frameworks that allow us to do that allow us to predict this type of behavior. And this is an example that I wanted to show you because precisely in this experiment, Stefano Aime was able to show that this is a creeping gel where they had applied a stress and watched the system eventually start to flow. And as it was failing, right? And they could see that before the system actually fracturing, there is a precursor of the fracture and the failure of the system that will happen macroscopically in this microscopic motion. So the blue data is in fact the intensity of the amount of the non-affine motion that it's seen through the shear cell, and the red data are the macroscopic rheological response. So you can see that there is this connection to build. Of course, in the case of failure, a fracture, this is extremely exciting because now it makes me think of materials that I can design, where I can design failure, or where I can predict specifically failure before it actually develops, and I can cure or I can promote those phenomena to make new kind of metamaterial that have a whole range of time scales in them. But also because it's in general, having access to this non-affine motion will provide all sorts of interesting information about how the system respond in the linear and in the nonlinear behavior. So in fact, I wanted to show you, I mentioned here on the bottom these other papers, and I wanted to comment about that because in fact, this type of experiments, have been recently also done, for example, through other type of scattering techniques, like for example, XPCS, which is X-ray photocorrelation spectroscopy, and there is a similar type of insight that you can gain, and in particularly, I would like to point you to the work of Jake Song in the group of Garrett McKinley and Gavin Donnelly in the group of Simon Rogers that in fact analyzed yielding and stress relaxation in nanoparticle gels and in more jammed soft solid to try to connect the non-affine motion, basically the non-affine dynamics that you can see through the scattering with the rheological response in terms of yielding and failure and stress relaxation. So on the right, I wanted to show you this because this is another way to extract this information about the non-affine motion. And here, the non-affine motion you can literally see. This is the experimental setup of my colleague here at Georgetown, Dan Blair, that has a confocal microscope mounted with this rheometer. So he can, in fact, image and these are again experiments over jammed emulsion, and he can image the displacement of the particles as it's been sheared in planes that are basically vorticity flow planes. And what you see is the motion of the particles in this very jam suspension that is being sheared. But what you're literally looking at is the non-affine motion. So what they took is that they were shearing the system, they subtracted the displacement, having measured the flow profile, they could literally subtract all the motion that would have been due simply to the material following finally the deformation. And this is what you're left with. And, at the beginning, it looks like, okay, this is just a little bit of bumpiness, the particles bumping to each other because, they're so jammed and you're forcing them to flow. This is a measurement that has been done in steady state. But in fact, if you stare at it for a bit, you can see that this is actually a very complex motion that has a multi-scale arrangement. And it's very spatially correlated. And it's really not just, it doesn't lead to a simple diffusive type of dynamics, but it's a very complex multi-scale dynamics, which is made of avalanches and it's a bursting type of dynamical activity. And I want to come back to this a bit. Okay, so in fact, a segue from this is that, in fact, these materials, basically, when they flow, it's always complicated. Some of this material, I wanted to highlight this because we often, refer to some of these materials as simple yield stress fluid, right? There is a stress that you need to overcome for the material to flow. And some of these materials, they really don't have any complex structure formation that it's due just to the deformation, or maybe they don't seem to significantly change over time or age as you don't apply any deformation. But then when you force them to flow, I would say we can call them simple, but the way they flow is always complex. And the fact that it's complex, it actually means something. Let me show you what I mean. Well, in fact, it's a whole range of materials, right? Where when we measure the stress as a function of the rate at which the material is flowing, once I overcome this stress, the stress at which the material is flowing, in fact, depends non-linearly on the rate at which I apply the deformation. I think you could have seen already this coming, but it is a point that I want to make, that in fact the rheological response of this type of material, it's always strain rate dependent, even when we deal with systems that are relatively well elastic, because when we start to break things and to induce plastic processes, then we also automatically induce the capability of the system to rearrange in a way that is non-trivial because of those stresses frozen in that I was discussing before. And so this produces a dependence of the stress at which the material flow on the rate, which is complex and emerges in this type of Herschel-Berkeley type of flow curve that we know it's common to a broad range of material. And the reason why it's common to a broad range of materials, it's because, in fact, this type of flow curve, if I think in terms of what are the microscopic processes that can lead to this type of flow curve, is in fact, it's been understood that in order to get this type of dependence of the stress on the rate at which I'm forcing the material to flow, for example, if I'm applying a rate, is by yielding locally, and then this through a localized plastic process, which then thanks to the stress or the partial stress relaxation that it produces, this triggers another plastic process farther away of that, which then trigger another plastic process farther away of that. And it's this avalanche that and this sequence of plastic rearrangement which depends one on each other and produce a overall very cooperative and collective phenomenon, strongly spatially correlated, which is underpinning this type of rheological flow curve. So we see this even in gels. This is from our simulation. And on the right, you see basically one of our gel model where I'm showing you just the network, the connections between the particles, because I want to highlight now what I'm doing in this type of visualization is that I'm measuring also the stress across the different part of the structure, and I'm drawing as thicker the regions where there is larger tensile stresses. And so the regions that, you start from this and the materials start to deform, and the parts that start to become thicker are regions where the stresses are higher. So you can see how the stress is localized in a tiny part of the structure. And then things get stretched out, and when they become blue, that's when they break. And when I break some of that, I have to redistribute my stresses. Maybe I can make some other connection somewhere else, but I have to redistribute these stresses in compatible with the structure that I'm also breaking or reforming. And so it's this type of dynamics that then leads to a devolution of the system. So how much I can form more bonds or may break more bonds and where will depend on the type of structural heterogeneity that I have to start with, will depend on this subset of my structure that actually transmit the stresses. And it will also depend on how fast or slow I'm going, because this will favor or not the reconnection and the relaxation of the stresses inside my system. And so, for example, you can see that as you go very low, you can produce things, you can in fact favor the fracturing of the system. This is what we see in this type of simulations, that actually when you are deforming the gel slower, you are promoting the densification of the gel in some part of the structure, which then triggers the formation of further connections as I keep shearing until I make some part of the gel stiffer and stiffer, and then and some part less and less connected until I'm able basically to break, and I produce some fracture plane through my gel that you can see basically here. So this type of dynamics is what we can see happening microscopically, and what should be in our head when we try to understand what's happening in the rheological response that we measure macroscopically. So when the part here, I was showing something that will happen on the right as I'm pushing the system, deforming the system until it starts to flow or it fracture. On the left, I was talking instead more of what happens even as the material now it's flowing in steady state with this type of correlated plastic avalanches actually are still at play. And at the point that when I stop the flow, things like this happen, right? So when I stop the flow, these are what people call flow cessation experiment. And these are experiments actually in this case that have been performed in several groups over the last years. This is a recent one with a group where from work I've been involved, and the experiments have been done in the group by of Veronique Trappe in University of Fribourg, and together with Marco Cagioni, Procter & Gamble. And so this is a model jammed soft solid that they have forced to flow, so it has this Herschel-Buckley type of rheological behavior. And now you stop at different points, at different rates, while the system is flowing at different rates, and you measure your stress relaxation. And so what you see here is the relaxation of the stresses divided by the initial stress and plotted as a function of the time times the rate at which the system was flowing. So you can really see that this relaxation, in fact, depends on the rate at which the system is flowing. So when I stop the flow, there is a memory of what the system was doing before stopping the flow. And this is not due to the inertia of the rheometer. It's, it's in a condition in which we have been able to exclude all those effects. So it's really the dynamic, the relaxation dynamic of the system, that it's doing something that in fact depends on the rate at which the system was flowing. And the stresses relax down to a value that in fact is non-zero. So they don't relax completely. So that people refer to them as residual stresses. But even the value of the residual stresses depends on the rate. And in fact, as you can see in this central plot, depends on both the rate and, for example, the dissipation. Here, this is the experiments were done with different viscosities of the solvent. So you can see that, in fact, the viscous stress that was developed during the flow, it's what seems to control the final residual stresses. And in the inset, in these two plots, you have, in fact, the same measurement, the same test done in a simulation in the same kind of jammed soft solid that I was showing you before. This is on the right. These are experiments in the group of Michel Cloître and Roger Boncaz, where they studied exactly this type of phenomenon a few years ago. And there is also more activities in this area. So I suggest you follow this type of developments, because people are really trying to understand what's happening in this system as this type of phenomena emerge. And if I manage, I want to tell you a couple of things about this. But in fact, it's also very interesting then, as you explore more complex systems, it seems that this stress relaxation, when you stop the flow, can become even more complex. I guess, and these are cases from recent experiments where people have seen, in fact, even non-monotonic stress relaxation. So the time scale that have been embedded in the system not only depend on the rate, but they seem to lead to development of structure at different time scales, which is maybe one mechanism that could lead to this non-monotonic stress relaxation that in fact has been seen, if I understand correctly, mainly in associating systems. So now the case I was showing you before up here, these were systems that were mainly just done of soft squishy particles that were pressed into each other. So that's how the system was solid. Whereas in these cases on the bottom right, these are systems that can aggregate like the gels we were talking about before and form different type of multi-scale structures, which then maybe could lead to this type of complex stress relaxations, which still require to be understood deeper. Okay. So nobody asked question so far. But I'm happy to take a pause and to answer questions if people have them. Just to conclude this first part, what I want to tell you about, it's in particular what is the way we look at these problems and what is that we're trying to do, how to combine these microscopic insights with the macroscopic rheological behavior. But before going into that, I'm happy to take questions if people have them.
Well, I'll start. I'll break the ice for the first question. Can you, actually it's more maybe a misunderstanding from me. Can you show back again the movie with the network, please?
Yes. Just a sec. Yes.
So here, each line is what exactly?
So each line is either a connection between two particles or a connection between multiple particles. It could be a branch of my network.
And here the shear is, so the top is going to the right and the bottom is going to the left.
Yes, yes, yes. You don't see it because I, put everything back in the box so that
Yeah, sure. But like, why are, I mean, I'm used to build these kind of networks, and usually all these lines go in the build on the axis of compression. Here they seem to be in the dilatation axis.
because this is a system that it's really made of two-sided springs, right? So actually the structure can be stretched and
Okay,
can
so that,
right? Because this is really an interesting difference between this type of networks that you get in these gels versus the networks that you would get, the force network that you would see in suspensions of repulsive grains or particles, right? That those networks, the contact, the network can still have some complex behavior, but the contact, in that case, they do not resist tension, right? Because
sure.
there is, whereas in this case, they do. Because I literally have, attractive interactions between the particles. So there is like a little spring. And what you see here, these structures that align, this thicker, tense structure that align is because basically there is a region of the gel that I can stretch a lot. And then once that I stretch them out, I start to pull really on the connection between the particles. And this, in fact, produces a stiffening of the response due to the fact that now I'm pulling something that it's really much less deformable with respect to the floppy gel that I had in the beginning. Right.
We
And so,
also, sorry, go ahead.
no, that's, I think that's fine.
Just there is a question in the chat. Athanasio is asking, are the fluctuations in the blue curve of stress relaxation left panel simulation artifact or avalanche behavior? So I think it's the last slide you showed before with the stress relaxation. Yes.
You mean the non-monotonic behavior?
The fluctuations in the blue curve, yes. And
So
in
there
the
are several
simulations,
blue curves.
in the
In this,
simulations, so the
in
fluctuations
this,
in the blue curve in the simulations, is that artifact or avalanche behavior?
I think it's avalanche behavior, but of course, this. I mean, we know that there are avalanches there happening. I didn't include a movie here, but in fact, one can see them. There is always the question then of then increase, in this type of simulations, increasing the system size and some effects that could come from limited system size. In this case, the simulations are around 100,000 particles. So the system is not too small, right? And if we analyze spatially the dynamics, we can see avalanches of rearrangement of the particle packing, basically.
We have another question. Is the stress cycling experiments of Perj-Manville et al. Where the gel fluid as in steps, is it correct to think of it as fatigue? If yes, what do we get the third step? So it's back in the stress cycling experiments. Yeah.
Now I realized where I should look for the chat so I can see it. Thank you.
Oh, okay, great.
Yeah, and so and that's exactly the question, right? In the sense that the fact that there are several steps, right? It clarifies that it's not just okay, there is one type of connection that I need to break, and now my system is fluid. But there is still some hierarchy of connection, of mechanical connection in my structure that I have access to when I cycle the stress. And, it could be structures that I reform as I'm cycling. So I am weakening certain parts of the structure, or while I am actually stiffening some other and building up some other part of the structure. Where does this happen? I think it's a very, very interesting question. And how does this depend on the architecture of the network that you start with? I think this is a very, very interesting question that, in fact, I would like to try to tackle. But there are other people that are studying, that are investigating in this direction as well. I think we don't understand this completely, but it's evidence of that. So if I think about, the fatigue that I see, are certain parts of the microstructure that, in fact, I can protect and induce and, in fact, make more robust by cycling my material, are other parts that I'm actually breaking, and which are those. So I imagine that if I was able to do that and to control that, I would be able to use these materials, to learn, to compute, to do all sorts of very, very interesting things that could, could be, in fact, produce a very, very rich type of metamaterial behavior.
I guess you can see that
Yes,
they're
I can.
thanking you.
So
We have 2 more questions here.
Does the model include bending forces among different chains? Yeah, in that case, we do have bending forces. But I am not sure that it's the contact. I will come back to that later. But the contact between the particle, in our case, in the model that we have studied there, contains also bending effects. But I could also study a gel. I think that I could also study a gel without having that type of contact. But then the larger scale structure that it's formed through the aggregation will develop some bending stiffness on some larger length scale, right? And so at a coarse grain level, I think I would see something similar, even in without that type of specific ingredient.
Okay.
I don't see other.
I think you talked about the image and slide of strain localization, which shows elastic event, plastic event, right? The question from
The story of the
yeah. Okay.
Yeah, I think, or maybe I'm missing some. Can you please explain image one slide of strain localization, which shows the elastic event and plastic event? Yes, sorry, I didn't explain that. You mean this one on the left bottom, right? So this is basically a cartoon that I think it's very effective. It's from this book, this paper of Liderik Bouquet, Kirsten Martensen, where they provide a cartoon of how this would happen, right? So as you are sharing your system, there is in fact a location where some plasticity can develop. So maybe as this part that it's where I had some stress heterogeneities that I was mentioning before, where my spring is stretched or it's compressed, and there is some possibility to rearrange. And so then when I do that, so I have this plastic event, the plastic event will in fact, and this is, the cartoon in the center show you how the local packing of the particles in fact has changed, and they have exchanged neighbors. In this context, this would be my plastic event. This produces some stress relaxation, which then propagates through the structure because it's elastic, and then it's able to activate another plastic event somewhere else in the material. And then there, the same thing happens. I have some relaxation, which then activates another plastic event somewhere else. And that's actually how my material flows, right? Which is very different from what we would first imagine. But I think it's very important to think in these terms. When people want to read more, of course, I mentioned this paper, there is the Rheology paper, which is, where this model was introduced that produces the Herschel-Balkley type of flow curve. One reference that I like very much is the lecture notes of Armand that you can find on the archive from Les Houches summer school in 2002, where it goes over some very big basic questions about this type of behaviors and basic ideas about this type of behaviors. Recently, there is a very nice and comprehensive review paper from the Grenoble group by Jean-Louis Baraki, Esther Martens, and Alexandre Nicolai, Ezequiel Ferrero, which provides a very broad overview of elastoplastic models, as they are called.
Great, thank you.
In fact, I haven't done this for this lecture, but one thing that I can do if people are interested, and I encourage them to write to me or maybe write to you, and I can do that, is to provide a list of further reading related to the topics that I am going through. So I hope that, of course, this is my personal selection and it's not meant to be exhaustive by any means, but it could be a good are just some suggestions for reading if people want to know more about
Well, it would
this.
be great to have it in any case, so we can just add it to the YouTube description of this video. Okay, great.
Okay, so I said that I wanted to once that I have set this scene of these questions and very interesting phenomena that are, if you want, in my mind continuously as I think about the rheology of these systems, and as I try to understand how to predict the rheological, this type of rheological behavior, understand the connections between these different aspects. The way I'm thinking about this is basically thinking from my side that I would really like to be able to build this loop between the microstructure that the material has, the way it responds to stresses, and how the stresses produce deformation, which then changes the microstructure, and so on and so forth. Because this is what the rheologists is about. Right. And no matter if I'm doing, my bulk rheology characterization in the lab, or I'm trying to 3D print a new material, these are questions. This is the question that is at the core of everything. And this is what we are basically what drives a lot of the research that we do. And I think a lot of research that is emerging really in these years. And so one way to think about that is to say, okay, I have, the stresses my system is going to be related to the rate at which, the system is deformed, and so the velocity fields in microscopically, but also it comes from the microstructure, right? Which then it depends on the forces, as we were discussing with Michelle, the forces between the particles then will determine if stresses are going to be tensile or compressive, and the way the microstructure rearrange. And so that my perspective on this, what I'm particularly interested is really thinking about the microstructure and the microscopic degrees of freedom, and thinking about how then the stresses emerges from this degree of freedom. We would like to be able to see this emerge in the simulation so that we can gain some fundamental physical understanding of then where does the rheological response come from. And this is what you need for the next constitutive model that we need to build. But I'm not, by no means, I'm the only one doing this. There is a range of different groups that have been working and with a similar mission, and I encourage you to look in their work. And by no means this is exhaustive, during the thing. So what we concentrate a lot on is the part that comes from the microstructure, right? And because in this type of system, the behavior that I was describing, it's really characteristics of systems that are very strongly interacting. So in many cases, we can get away with describing, let's say, the flow of the solvent, the hydrodynamics of the solvent in a relatively simple way. And instead, we put a lot of effort in trying to understand the many-body physics of how the stresses emerge from the microstructure. And so the idea, for example, is that if I have a model for the interactions between my particle, then I can extract the forces and I can construct the stresses. The approach that we use is that we solve the microscopic equation of motion for all this degree of freedom, so that as, for example, there is a deformation that is imposed or a stress that is imposed, we can get the evolution of all the particles that are part of the material, at least that we can capture in the simulations. And so we obtain a full spatiotemporal distribution. So we have access to the non-affine motion that I was describing before. We have access to the evolution of the stresses as a result of the interplay between the microstructure and the deformation of the stress that we apply. And this is what we are basically trying to do. And I think it's an exciting time to try to do that, especially because combined with the experiments that I was mentioning before, the type of experiments, not only the experiments I was mentioning, but much broader, the type of experiment in which you can try to combine rheology with imaging or spectroscopy to actually gain understanding and insight into what is happening microscopically. And the level of understanding of the theories and the constitutive models that allows us now, for example, to know how important are surface contacts between the particles, and how important and how complex can be the range of length scales that have to be involved. How important it is to have a tensorial description of my system, because I really need to capture this large scale heterogeneities and the deformability of the system over different length scales. Okay, so basically, this was my part one, and the hour is nearly gone. So if I can, I would like to tell you a bit about point 2 and about point 3, and I will try to keep it short so that we have maybe another few minutes for questions and for wrapping up before I finish. But please continue ask questions and just let me know, because I prefer to have that we clarify ideas as I'm discussing them, rather than having to get to the bottom line. I really don't care. Okay.
I think it looks like a perfect plan, and we're all here to hear you. So
Perfect.
that's perfect.
So yeah, so let me say something about something else that I would like to add about, in particular, the particulate gels. I want to say that this does not necessarily apply only to the particulate gels, but I connect it to the particulate gel because I think that here we can see very clearly how this is important. So basically, I'm thinking of materials that have this type of very complex structure. I showed you before this image on the left, but you can have much messier gels like the one in the center or on the right. And the reason is because there is a whole set of complex phenomena that can lead to the formation of these type of structures. There is disorder, there is different type of aggregation on different length scales, and this produces structures that are porous, that are complex on several length scales. So, when thinking in terms of colloidal particles, like the model ones that I was showing from, like the model system that I was telling you about from Mike Solomon experiment, I think that in fact there is a well-established way to understand, for example, the phase diagram of this system. So if I have a suspensions of particles and I know the physical chemistry of the suspension, so the particles, the surfaces, the solvent, then in fact I have some tools to predict predict when the particles will aggregate, when they will tend to form, for example, even crystalline solids, when they will tend to form glasses, and so on. And so these are examples of phase diagrams that people have drawn or measured from experiments to make sense of where actually the gel is more, these type of gels are more likely to form, because in order to get a gel, I need a strong interaction. So they will tend to be along, for example, this phase boundary between, phases of clusters or of liquids, really dense liquid of particles that tends to nearly phase separate from the solvent. And these are basically equilibrium. So I have the equilibrium physics that allows me to understand the phase diagram, because these are equilibrium, it's an equilibrium phase diagram. And then I have this non-equilibrium states, which are the gel that develops in this type of equilibrium phase diagram. Basically, the equilibrium phenomena, that is the aggregation, the phase separation, the microphase separation, they trigger the formation of the gel because they provide the type of structures that then can gel. In other cases, I will have completely non-equilibrium processes like fractal aggregation, diffusion limited type of aggregation, basically where the particles, they stick together and the interactions are so strong they just remain stick. They don't try to explore their equilibrium states. They do not have the possibility to explore their equilibrium state. And so then in all these cases, however, I will say that the structures of the gel in the end is the result of this part of this initial aggregations, which has started in different ways, but then gets aggregation and growth that then gets frustrated into the structure of the gel, where basically these stresses accumulate, as I was describing before with my little distorted network of springs. So I can see in this type of phenomena how that stress localization and how the Frozen stresses can emerge. So what I want to, I will maybe jump ahead of this, because what I would like to show you is a situation in which, I would like to make this point, because you may think, okay, what you are describing is something very complex and very messy, and in the end, it's interesting, but what are the hope to be able to understand something like that? And so that's why I wanted to show you this, which is a very interesting example, how these are a study in which we have looked into several types of these gels formed in a model in a computer, and you can see the networks on the right, examples of these networks. This is the rheological response. We measure the tan delta here, it's the ratio between G double prime and G prime as a function of the frequency. And as we vary the volume fraction or the kinetics of the aggregation in the simulation, this tan delta goes all over the place. However, you can in fact construct a master curve of all this rheological behavior, which is actually very interesting. So, you can shift the frequency in this plot on the left to make your tan delta basically overlap into a unique master curve for all of these gels. And you can, and then once that you have this horizontal shift of the frequency, you can keep that shift and shift only the y-axis to obtain a unique master curve of all of the whole rheological spectra. And what is interesting in doing that is that, in fact, we understand what's in this type of study, what is the microscopic origin of these time scales and these energy scales that we have to put in. And we realize that we can demonstrate that they are associated to a hierarchy of mechanical elements that constitute the response of my gels. And this hierarchy of mechanical elements, they come from the way the gel forms, but they are not easily visible in the structure, because the structure is actually too complicated to see that. But the rheology, in fact, allows us to see clearly that there is a backbone structure that in fact is fractal, and it's embedded in the structure of the gel that develops as the gel gains rigidity, and it controls the rheological response. What is very interesting in this master curve is that if I try to fit it with, spring and dashpot type of elements, I realize that not only I need a huge amount of them, so this is a response that is extremely complex, but in fact, I need to have them arranged in a very specific way, in this ladder-like way. So I really need this huge amount of elements, but even more important, I need them to have them arranged hierarchically in order to reproduce the rheological response of this type of gels. So my gel, they look messy, they look all over the place, but in fact, they are a collection of elementary elements, which is the part of the structure that controls the rheology. And so there is a way, in fact, to understand this type of behavior. And I think with this, I would better, I don't want to enter this, but I think I want to conclude, rather, to leave another couple of minutes for questions. And I thank you for your attention. Let me go to my summary.
I think everybody here is reading your summary.
Sorry, I can help.
No problem.
So basically, I wanted to highlight how it is important to understand the disorder and the structural heterogeneities and the stress heterogeneities. Without this, we cannot make sense of the rheology. And in fact, when we do this, we realize that even when we image all the structure, we need to understand what is the subset of the structure that in fact controls the rheological response. And this is crucial to identify what are the regions where, or it's completely connected to identifying where are the regions where strain is localized, where stress is localized. And some of this information is contained in the non-affine motion. Therefore, combination of experiments with simulations and experiments of rheology with imaging and experiments, combination of rheology with spectroscopy, with different type of constitutive models are the direction to go in order to understand if you want to exploit the potential of this type of materials fully. I told you a bit about how these particulate gels can be complex, but also how we can, in fact, find a way to rationalize overall the rheological response. And I didn't tell you about just a little bit about what, the yielding and the flow and the plasticity, and that is even translating in the behavior under flow cessation of, in general, soft jammed materials. But this is a direction I'm currently working on, and I'm happy to provide further reading suggestions also on this part, even if we didn't get to go through that. Thank you.
Well, thank you, Emanuela. Are there any questions? Okay, so we have already a question. So can you please tell something using a thermal quasi-static shear deformation, how it affects the structure, how it is different from the system it is under continuous deformation?
So this is a very interesting question. The image of the gel that I was showing before, it is some version of a thermal quasi-static, but it's not quite. So in a thermal quasi-static, what you do is that you apply, so you simulate or you represent the behavior of the deformation, the behavior of the system under deformation by applying a small step, of deformation. Right? And then you let the system find its closest minimum. Usually this is used, it is used the conjugate gradient to do that in the calculation. And then you apply another step, and then you do conjugate gradient, and so on and so forth. And the idea is that when you, for example, when you simulate a system under continuous shear, the rate that probably you can afford to do in the simulation is pretty fast and does not represent necessarily well enough what would happen in a real system where I'm applying the deformation from the boundary, and there is, all the rates that I can use in my rheometer are relatively slower than what I would do in my simulation. So there is a lot of opportunity for the microscopic dynamics of the system to then enter and determine the response of the system. Whereas if I'm going too fast, it's just the deformation rate that will dominate everything. Most of my motion will be fine, and so I don't capture really what's happening in the experiments. So in this type of, in the thermal quasi-static shear was introduced to try to mimic the fact that the system is actually able to reach a local minimum before I continue shear. Okay, so the problem, the thing to pay attention when I do continuum shear is to think if what I'm seeing is representative enough of the dynamic that I should be seeing, because in fact the system has the time to explore its potential energy landscape. In the movies that I was showing you of the gel, we were doing something like that, but slightly different. The drawback of the thermal quasi-static shear is that I am assuming that minimization that I do with the conjugate gradient actually corresponds to some real dynamics. Actually, I'm not assuming that, but the question is there. Is that representative of a real relaxation dynamic in the system? Just the direct path into the closest minimum that I can find with the conjugate gradient. In our simulations with the gels and also with the JAM system, you can really see that this is not the case, that there is a range of dynamics that I can explore that would be more representative of a finite rate deformation. And so what we do is that we use a combination of a thermal quasi-static shear and dynamics to explore that. Basically, we apply again a small step in the same spirit of a thermal quasi-static shear, and then we let the system relax the stresses through a more realistic dynamics to explore basically its energy landscape in a more realistic way. And this is important because the energy landscape of these systems, no matter if these very soft gels or the jammed, very dense systems, it's very complex with many minima, but especially many flat directions. And so the being able to actually sample some of those flat direction, it has a big impact in the type of dynamics that you see, and then in the type of rheology that emerges from that. I hope I managed to at least address some of the doubts of the person.
Well, it seemed to me a very exhaustive answer. Are there any other questions? Okay, so I don't see any more questions on the... Well, I had a couple of questions, but I don't want to take too much of your time, also because it was mainly on the slides about the rigidity development.
Mm-hmm.
And I guess there were some notions about the how you detect those rigid structures from multiple ways of doing that. So, but I'm not gonna, I mean, I'm curious, so we could have maybe another chat in a second time, because that would be...
I'm very happy to do that. And also if people want to reach out to me, if they have a specific question that they want to ask. There is one thing that I want to say about the rigidity story, that I am really thinking about the rigidity has an organizing principle for this type of structure. And it can be an organization that happen, of course, under certain type of constraints. The constraints are provided by the interactions, by the path through which, for example, a gel goes, or it could be provided by, the constraints are provided by the flow. Let's say if we're thinking about things like shear thickening, or the constraint is provided by the fact that the stresses have relaxed or have found some optimal local minimum, if you want. And this larger scale organization, which is coupled with gaining rigidity, losing rigidity, regaining rigidity. That's, to me, it's very interesting right now.
I can't agree more. Okay. If there are no more questions, I'm gonna stop the recording here.